of you, respected Honorable Vice Chancellor Sir, and all our learned panelists. So, welcome to the webinar Development of New Generation Ceramic Materials, organized by School of Energy and Environmental Sciences. So, we are actually organizing this kind of webinar from back in June. So, today is one of the webinars which are on new generation ceramic materials. So without wasting time, I am requesting our Professor Tapan Kumar Padia, Sir, Director, School of Energy and Environmental Sciences, to deliver the introductory speech. Sir, over to you.
Honorable Vice Chancellor, Sir, Honorable Academic Advisor, Sir, distinguished resource person, Dr. A.K. Chattopadhyay, ex-Managing Director, TRL Kurosaki Limited, now Managing Director of National Refractories, two young dedicated researchers come panelists of the day, Dr. Palash Kumar Haldar and Dr. Souvik De, respected faculty members and colleagues, dear participants and beloved students. Very good evening to everybody. At first, on behalf of Makaut and School of Energy and Environmental Science, myself, Professor T.K. Padia, wish to convey sincere thanks and profound greetings to all of you for your kind participation in this webinar entitled Development of New Generation Ceramic Materials. It is indeed my great honor and proud privilege to heartily welcome you all in the webinar on such a fascinating subject. In fact, the School of Energy and Environmental Science becomes highly encouraged and motivated to organize the webinar under the constant inspiration and valuable guidance of our dynamic Vice Chancellor, Professor Suikoit Moitro, expressing our special gratitude and indebtedness to you, sir. In course of the program, our Honorable Vice Chancellor, sir, and Dr. Arup Kumar Chattopadhyay, both as renowned academician, well-known industry personality, and material technologist, will highlight and share their vast expertise and valuable experience on the huge prospects, inherent challenges, and potential applications of the new generation advanced ceramics. Two young talented researchers, Dr. Palash Kumar Haldar and Dr. Souvik De, will discuss and share their innovative ideas and research experience on the generation of the transition metal doped zinc aluminate spinel ceramics and muellite ceramics based on indigenous starting materials respectively. Both of them have carried out their research works under my guidance and recently been awarded with PhD degree in ceramic technology from University of Calcutta. Warm congratulations and heartiest thanks to you. In addition to traditional ceramics like terracotta pots, handicrafts, earthenwares, and utensils for domestic use, traditional refractories, common abrasives, cement, and common glasses, ceramic technology has progressed to a new height from 20th century onwards to produce sparkling bone china crockeries, exotic color sanitary wares, multicolored vitrified floor tiles, decorative glazed wall tiles, extra high voltage electrical insulators, super hard abrasives, and specialized ceramics for multifarious applications. These advanced ceramic materials at present have established themselves as the most promising materials for next generation automotives, electrical, electronics, conductive, magnetic, optical, defense, aerospace, structural engineering, metallurgical, computers, nuclear, communications, medical, green energy, and clean environment fields. Advanced ceramics are classified into four main categories based on their composition and crystallinity, as aluminosilicates, which include porcelain, muellite, cordierite, glass ceramics, glass, mass, jas ceramics, and machinable glass ceramics. Pure oxides, as for example, alumina, zirconia, magnesia, zinc oxide varistors, aluminum titanates, partially stabilized zirconia, magnesia aluminate, zinc aluminate spinels, perovskite barium titanate, zinc zircon titanate, piezo materials, PTC and TC thermistors and sensors, and bioceramics, etc. Non-oxides includes carbides like boron carbide, silicon carbide, tantalum carbide, tungsten carbide, graphite, carbon nanotubes, coating, C carbon fiber, borides, nitrides, boron nitride, silicon nitride, and aluminum nitrides, and as silicides, molybdenum disilicides. As composites, particularly reinforced composites based on ceramic polymer hybrid membranes, cermates, combination of the oxide-oxide, oxide-non-oxide, such as zirconia muellite, zirconia aluminum, alumina chloride, silicon nitride bonded silicon carbide, cyanide, tungsten, graphene, and polyaniline based composites for use in supercapacitor applications. Amorphous ceramics, fused silica glass, pyrex glass, lead oxide crystal glass, aluminosilicate glass for high temperature applications, toughened glass, germanium oxide, fiber optic glass, machinable phosphate glass, laser glass, ophthalmic optical glass, bioactive henge glass, and color glasses. Each of the classes can develop unique properties, leading to significant improvement of performance, behavior, service life, as well as the cost effectiveness. They may be used as bulk materials or as coating materials on the substrate. Pure oxide ceramics are characterized by high refractoriness, excellent abrasion and oxidation resistance, excellent hot stain, chemical inertness, electrical insulating, low thermal conductivity behavior. Non-oxide ceramics have extremely high hardness, chemical inertness, high thermal conductivity, and electrical conducting characteristics. Ceramic matrix composites possess high toughness, high oxidation resistance, but variable thermal and electrical conductivity. Advanced ceramics usually involves complex manufacturing process and high cost of production. High purity synthetic materials, precise methods of production must be employed to ensure desired properties in that products. The selection of the raw materials, formulation, mixing, fabrication, firing environment, finishing to finish, precise tolerances play a crucial role when designing structures, components, and devices based on advanced ceramics are selected. I strongly recommend for strong and vibrant industry institute interaction and active collaboration for creation and advancement of newer knowledge base, for newer pathways and directions towards future research and development activities. Under the heavy threat of devastating COVID-19 pandemic for last 1 year, the academic world is perhaps worst affected in terms of teaching, learning, and research outcome. However, teachers, students, community have been fighting very hard to keep themselves updated and apprised thanks to the several online courses and symposia provided by the leading universities, IITs, NITs, Indian Institute of Management, Coursera, MHRD, NPTEL, etc. through different online platforms. This has immensely created a new era of hope and aspiration amongst the young blood. At last, the great researchers are succeeded in the discovery of much needed vaccine for deadly virus. The mankind is now blessed with and confident of speedy restoration of the normal activities in all fronts through due vaccination. Academic world will be happy enough to accept and follow both ways of teaching, learning process, online and offline in their future endeavor. To conclude, the vast areas of the high-tech materials development technology are becoming synchronized, integrated, and smarter day by day in respect of material chemistry, crystallographic, assemblies, microstructural features, and optimization of the tailor-made properties. Thanks to the untiring and dedicated research works of scientists, technologists, supported by policymakers, which will actively drive the world towards a beautiful place of living for future generations. I wish the grand success of the webinar. Thank you so much. Once more, stay safe and be healthy. Namaskar. Over to.
Thank you, sir. Thank you for your courageous speech. So now we are moving towards our next speaker. So now I would request our Honorable Vice Chancellor, Professor Dr. Shoykot Moitra sir, to deliver the keynote speech of this evening. Sir.
Actually, first of all, let me complete the formalities. Good evening to all these distinguished speakers, particularly Dr. Chattopadhyay, Professor Fourier, Professor T.K. Paria, and two new speakers who have joined today. We were all informed that they just completed their PhD under the guidance of Professor T.K. Paria, Dr. Pola Shaldar, and Dr. Shobhik Dev. And there's Dr. Ananto Das is also here. So yes. He is not visible now. And Sri Kunal Chaudhuri and all the participants. So this is a great occasion in this sense that for the first time from the university, probably a webinar on this materials, high-tech materials, with an emphasis on applications in refractories and high energy areas. This is being organized. So from these things, from this perspective, it is an historical occasion, and we are just discussing that we need to take it forward for a generation of further knowledges, and with the development of a massive network and integration and collaborations amongst the knowledge community for the benefit of our researchers, our students, our personnel, professionals associated with industries and in other areas. Now, if we, the topic is today, I think is smart materials or high energy materials, whatever it is. This now entire things is being changed. And what we are observing now that in near future we have to migrate to another different sort of industry culture, which we call industry 4.0. And yesterday, probably you have read that 5G network has started in India, that one of the mobile operator, Airtel, they have started working on it. And very soon by 2021-22, within this period, we will have access to 5G network. But this is, this is creating an abundance of opportunities in terms of, this migration towards industry 4.0. This is a entirely, quantum shift. Starting when this industry first started with the advent of steam and machineries, migrated from 1.0 to then electrical energy 2.0, then electronics 3.0, and computer application. And now this basically machine and man interface and a massive, these interventions of artificial intelligence, robotics, data analytics, and all these things, these are going to, this becoming the predominating feature of all the manufacturing sectors. What is the outcome of it? Outcome of it is, in all the sectors and these materials manufacturing, refractory industries, ceramic industries, water industries, these will be under the ambit of industry 4.0. Already we have seen this has happened in glass industries, but this has not yet been matured. By 2023-24, the scenario, the entire industrial scenario will be, attaining a level of maturity in terms of, this embracing and absorbing industry 4.0 techniques and cultures. So precise control of manufacturing and material properties and all these things, this is going to be features of the future. And at the same time, you say this, one of the major problem of ceramic materials is we have to deal this all this material manufacturing when the materials are coming from natural raw materials. Then the problem is the heterogeneity. The raw materials varies from places to places, and we need to beneficiate it, we need to purify it, and then sometimes it can be used as it is, but most of the times it needs further beneficiation, further purification. We need to use synthetic material as well. But whatever it is, in all materials, in terms of this level of this contaminations or impurity or presence of other components, if we look into all these things, this cannot be this uniform everywhere. But in near future, with the applications of this artificial intelligence enabled processing techniques and machineries, that will be this serving the purpose of making the entire production process, manufacturing, quality controls, and all these things more homogeneous, and this more quality producing. This is one thing. Second is there will be a change in the manufacturing processes altogether, and at the same time, abundance of opportunities will be created. So this is the right time to see how best the people of other places who are a little bit advanced compared to us, how they are aligning themselves to the changing scenario. Because as everything has been changed, and the culture of this different, this personalization, customization, all these things are coming. How all these things, how these standard processes and all these things, how it is being this adopted in manufacturing sectors, how our technologies, they are aligning, they are adopting all these things by reskilling themselves with proper these inputs from artificial intelligence, data handling, data analysis, data analytics, and then those, machine learnings and all these things. And I believe that within near future that there will be a paradigm shift in manufacturing sectors, in education sectors, in our attitudes, and in everything. In keeping ourselves aligned with the changing scenario and the disruptive worlds, we have to embrace these transformative changes, and this is the future. So from our side, I was discussing that we are planning to organize these types of, this knowledge generation, because this is very much required now. The entire world, COVID, one of the major takeaway from this COVID-19 period is we became more and more accustomed to digital culture. Already there was a writing on the wall that the entire things is getting transformed after 2013-14, when people are talking about application of artificial intelligence in many areas. We were a little bit, this complacent and not so, this prepared for getting ourselves changed to that directions. But COVID-19 forced us to make ourselves changed in a particular, in the directions of this disruptive digital transformation. So this is this is the time where we have to gather, this knowledge. We have to get opinion. We have to look at the opinions of other people, how they are, adopting to all these things, and then this development of knowledge community for sustainability of all these things. This can happen in the near future, and with that purpose, we are going to organize a series of these webinars in material researches, material innovations, because material is going to be one of the key component of the entire industry process, because it may be refractory material, it may be polymers, it may be composites, it may be this material glass, it may be materials of different types. There will be phenomenal this evolution in all these material applications, material manufacturing process, material designing, material developments, and there will be tremendous opportunities for our research communities, for our this industry people, for people who are going to apply their innovative knowledge for entrepreneurship and all these things. How best that can be done? So we need to look into it. I can say some of the examples, like now, for example, the sanitary wares of the future. If it comes to the market in a wider scale, already in certain places people are working on it. It will have the sensors embedded in it with the different for different purposes, which will monitor the health of the persons who are using all these sanitary wares. This is one of the things, and that will be an integrated this effort. All this captured data that can be translated to through cloud to the medical centers, and from there preventive measures, prognostic measures, all these things that can be taken. Even for all these the ceramic wares which are used for this keeping some things warm and all these things, optimum heat content, keeping the this temperature level at the optimal level conducive for our health and all these things, that will happen, and that have already started. That have also started to come in the market, and there are significant amounts of researchers going on for continuous this development of the quality of products and application of the products for different purposes. Refractory materials, for refractory materials also. These types of practices, I am not quite informed, but probably it is being happened. It is being this happening at other places. We are not. I am not aware. But how people are doing this, how they are doing or taking up all these these things in the manufacturing system, all these things we want to know, and based on that we want to revise our curriculum. We want to revise our training program. We want to this make our future generation suitably reskilled with proper sets of knowledge, skill, and ability to take up the challenges of the future. So with this, I would like to conclude, because I cannot contribute much this in throwing light to the present status of the materials. So Dr. Chattopadhyay is the right person here. He can share his wide knowledge and experiences and wisdom in this area, and what he is foreseeing about the future. That is very important. That will be very interesting to us to listen. And at the same time, our young researchers, Dr. Paula Shaldar, Dr. Shobhik Dev, what are their opinions to, because they have completed their PhD works, but thing is this, how the future is changing and how best you are planning to embrace the changed future. That also will be interesting for, quite interesting for us to learn from you. And with this, I would like to conclude. Thank you, Professor Paria, for organizing this webinar for the first time. But I believe that in near future, within the shortest period of time, we will have more numbers of webinar. Dr. Chattopadhyay will be there. So we can plan to organize in such a way that the people from this other institute or the top-notch universities and industries, they will come forward to share their views. That will really help us in our academic exercises. Thank you very much.
Thank you, sir. Thank you for your detailed technical speech. So now moving towards our next speaker. Our next speaker is Dr. Arup Kumar Chattopadhyay, Managing Director, National Refractories. So, sir will speak on smart ceramic materials. Sir,
Yeah,
over to you.
thank you very much. First of all, my congratulations to two young scientists, Dr. Souvik Dey and Dr. Polas Haldar, for their achievement, and my heartiest congratulations to them. Then I must compliment, first of all, Vice Chancellor of Makaut, Professor Soikot Moitro, for giving this vision that these kind of things can be organized, and Dr. TK Paria, and of course my professor, who is also sitting here, Professor B. Paira, under whom in late 70s I was taught. Whatever today I'm thankful to all of them because of their contribution and their hand-holding. We are here today. And I'm in this industry for last 46 years. Of course, seen so many ups and downs. Mainly my tenure was spent in refractories industry and related with mainly with steel. But nonetheless, we had always connection with materials and ceramic materials. Now, coming back to my topic today, that smart materials and smart ceramic materials. And I thought that what I should speak today in the evening, that what should be its role in creating a very sustainable future for our country. And when we are speaking of Prime Minister is talking highly about Atmanirbhar Bharat, it's absolutely essential because some of the raw materials in this industry is not available in this country, and we are solely dependent on many other foreign countries for these raw materials, which is not a very healthy sign. So we should concentrate, work on that area. Now, before coming to the subject, I would like to stay 1 minute with you. Why manufacturing is essential for the prosperity of a country. You know, and always we have seen that India is very good in service industry, India is very good in IT, but why manufacturing is important? Because manufacturing always create very sustainable employment opportunities with a greater multiplier effect. That is what is essential, and then it sparks innovation. And also it reduces the trade deficit of a country, of a nation, and it determines and improves the global competitiveness of a country. So from all these considerations, I would say that manufacturing is absolutely essential. Why we will progress on IT, will progress in service, but at the same time, we must progress in our manufacturing. And there, nothing can be better than the ceramic smart materials. I would like to take a few seconds for electronic system design and manufacturing, their data. What is today the market, Indian ESDM market? The analysis is that 2010, it was a market of 40 billion US dollar, which in 2015 gone to almost 65 billion US dollar. And last year it touched almost 100 billion US dollars. So this is progressing, but nothing compared to some of the developed countries like Japan or Europe, some of the countries. But nonetheless, we have made a good start. So this evening, I will talk on few things, mainly ceramics in communication, how ceramics is helping in communication, and high points of electronic ceramics, how ceramics and dielectric and microwave communicators, dielectric resonators. And to some extent, when we talk of resonators, we'll have to talk about microwave magnetic garnets also. Then I will touch upon few things in piezoelectric ceramics. And finally, I will end up that how ceramics is helping in our creating night vision technology. So this will be the topic, but as you know that this is a very big subject, and we cannot cover in 120 minutes or 30 minutes lecture. I will try to touch upon the few points which will create some amount of excitement with all of you. What are these things? Now we can't think without a mobile phone, without a digital camera, without a LCD monitors, set-top box, then inverters, servers, and all this will be there. Ceramics is playing a vital role. Our notebooks, notepads, base stations, digital instrument clusters, everywhere you talk of, all the substrates are made out of ceramics. Now, how ceramics have started in communication? That the functional ceramics were made more smart and intelligent, and there were early investigation on solid state electronics, and that were based on metal oxides and sulfides. Then properties were persuaded to have them shifted from conductive, means a metallic, semiconductor, and superconductor. And from there, we went up to dielectric, magnetic, piezoelectric, and electro-optic ceramics. And this was the development. Now, technical utilization of ceramics occurred in 4 different physical formats. One is a sintered polycrystals, second is single crystals, third is thin films, that is crystalline or epitaxial or suitable substrates. These were the development, and then composites in polymer or glass matrix or glass ceramics. So this was the development of technically utilizing the ceramics in the physical form. Then what was done? Sintering was done, crystal growth and thin film deposition were based on near equilibrium process maps, whereas composites are non-equilibrium mixed phases. Those were created. And then questions were asked by different people that do electronic ceramic material mostly center around all these subjects, or can ceramics talk? Can ceramic visualize? Can ceramic communicate? And the answer was yes. How? That is a high point in electronic ceramics. What has happened in the many unique and successful products emerged? That voltage dependent resistor, thermally sensitive resistor, fast ion solid state conductor, ceramic sensors, physical and chemical, that means biochemical sensors, including those for gaseous chemicals, magnetic ceramic spinel ferrites, rare earths, iron garnets, barium hexaferides as permanent magnets, ceramic powder for magnetic recording tapes. Ceramics were also used as dielectrics for capacitor, titanates as high permittivity. Titanates were always having very high permittivity, and ferroelectric media. Then came piezoelectric ceramics for acoustics and ultrasonic devices, including sonars. We call sonars because those were allowing us to develop a lot of acoustic systems. And then electro-optic and piezoelectric properties and transparent ceramics. Those transparent ceramics gave us opto and electro luminescent display material. And that is how industrial and commercial usage of these materials have started, by the sensors and these high points electronic ceramics. Now, ceramics were used for their dielectric behavior and in the microwave communication. Where were the 3 things? That one is the low permittivity. Low permittivity ceramic dielectric and insulators, where it was the index was ranging below 8. But then there were electrical porcelain. Those who were low permittivity, there the electronic permittivity value were less than 8. And those are the, just now Dr. Paria was talking of electrical porcelain, clay-based and talc-based. But then came medium permittivity ceramics, where electron permittivity was between 10 to 200, which were rutile ceramics, titania-based barium polytitanates, and low-loss capacitors, barium zinc titanate, microwave ceramics, dielectronic resonators, and these were all used as miniaturized oscillator for the simple form. Dielectric resonator as a ceramic cylinder of high permittivity when a standing electromagnetic wave to be sustained by reflection at ceramic air interface. Now, these were also not the highest end, because these were between 10 to 200 permittivity. And there's typical applications where cellular base stations, direct broadcast satellite receiver, police radar detectors where police uses, wireless cable TV, collision avoidance sensors, dielectric resonator antenna, molten detectors. So these were the uses of these materials, typical application of these ceramic dielectronic resonators. And a lot of filters were used for these electronics. But the last and the latest development is the high permittivity dielectric resonators, where frequency is between 0.8 to 32 gigahertz and low losses, very high Q value. Impurity contribution also very low. Temperature coefficient is almost plus minus 6 ppm per degree centigrade. And it should not contain any moisture, absorb any moisture, non-porous, totally densified. Porosity is and densification is such that it is greater than 99.5%. And restricted compositional choice. Of course, when I go to this kind of material, the choices will be very limited. And to the best of knowledge today, barium zinc tantalum, barium zinc cobalt niobium, zinc titanate molybdenum, and barium niobium titanium oxide. These are the only choices available for this type of materials. And then microwave substrates were used, alumina, and also microwave packages were made. Then we talk of thin-walled radomes, which are used for ceramic dielectrics and microwave communication. Finally, as I was telling, that these two are the classes where we didn't have permittivity, which is very high. But then high permittivity ceramics have also been developed and commercially used, which are more than 200 to 10,000. This is a modified, if AB is the total atom, then AbO3, dielectric with different AO-BO2 ratio. These are the two sets of iron, where A is lead, barium, strontium, calcium, magnesium, lanthanum, bismuth, and B is titanium, zirconia, niobium, tantalum, manganese, and tungsten. And there are relaxer types, PM and PZ, where lead, magnesium, niobium oxide. These are the materials where the ratios and substituents and dopants are all dependent on process condition. And these process conditions have created ferroelectric and paraelectric interconversions, nonlinear dielectric and optimal properties with very high P/E ratio, hysteresis loop created. And those are used as a microwave magnetic garnets. Microwave magnetic garnets are microwave propagation characteristics, those which are modified by a predetermined way by interaction between magnetic and electric field components. And this is, we call it magnetic and dielectric properties of the material. Certain ferrites with very high electrical resistivity and low magnetic loss and tangents lead to low insertion losses and sustained process losses with lot of unpaired electrons. Microwave devices like isolators, gyrators, phase shifters, circulators, all these devices operate as a consequence of ferromagnetic resonance. And these are the called microwave magnetic garnets. And the compounds here are yttrium iron garnet, Ye3Fe3O12, or Y3Fe2FeO4 having very anti-ferromagnetic coupling. Then we talk of substituted iron garnets, and hexaferrites like barium iron oxide based devices working to the high frequencies. These are the high frequencies up to 300 gigahertz. And these are the very high frequency, and these are used in the materials as seat absorber and reticulate foam absorbers, and in the aircraft, stealth aircraft. Then we talk about the piezoelectric ceramics, where we know that what is piezoelectric, where energy conversion is mechanical to electrical energy or converse. And piezoelectric ceramics, lead titania zirconate with morphotic boundary and with ferroelectric cells leading to hysteresis, and also electrorestrictive ceramic changes dimension under applied electric field without the hysteresis typical of relaxer type materials, which we are talking of just now. So this piezoelectric ceramics has also very wide application, but one of the thing I must tell here that there is a huge sintering problem of this piezoelectric ceramics, because lead containing ceramics, due to its high volatility and easy reduction to metallic lead by residual organics, and a relatively faster reaction rate of lead titania as compared to lead zirconia. And then there are other problems, but I'm talking of the problems because these are the problems which have been encountered in different laboratories in the worldwide, pulling problems across the Curie temperature, and importance of grain orientation in the polycrystalline piezo ceramics. Piezo ceramics, polymer composites. These are the fabrication difficulties which I was just talking about. And then what is the application of piezo ceramics? First, displacement transducer and accelerometer, actuator, acoustic and ultrasonic delay lines, fast-based filters, piezoelectric transformer, gas igniters, ultrasonic systems, sonic cleaning, metallic medical diagnosis, and SAW devices. So these are the application of piezo ceramics. And finally, I will talk of a few things about electro-optic ceramics, which are called transparent ceramics also due to double refraction. Electrical optical effects, small changes in refractive index caused by applied electric field, and linear dependence of N and E called pockets of effect exhibited by the tetragonal lead titanate, and highly transparent and polycrystalline ceramics that belongs to a group of lead zirconate and lead titanate and lanthanum oxide. And also the achieved by wet chemical processing followed by hot pressing, and these are the processes which are followed for wet pressing, and linear pockets have been formed. And electro-optic ceramics also have a huge area of application, like flash goggles for arc welding, eye disorder, nuclear flash, TV stereo viewing system, color filters, and image storage, thin film optical switches, second harmonic generator, frequency maximizers, and night vision, which is my last topic of this technology today, that ceramics in night vision technology, that people are using these detectors nowadays that you will not be visible. You are wearing a ceramic component and you will not be visible, but you can see the other people. So that is image intensification, they call. Very low levels of available light on striking the charged photocathode in a vacuum tube produces an electronics which then is multiplied by microchannel plate, causing a phosphor screen to illuminate. Low light TV. This is the commercial term now, low light TV. And active illumination, image intensified, is accompanied by illumination with bright source of NIR, where lambda is 0.8 to 1.2 micrometer, which the human eye cannot register, yet photoproducers can. And then there is a thermal imaging also. Thermal infrared, where lambda is 3 to 30 micron, emits by the objects differ in intensity, and which is picked up by a phased array, infrared detectors, and elements to create a temperature pattern called the thermogram. And there, the different generations of night vision devices depend upon the IR detector material used. That, like, we are just talking of 2G, 3G, 4G, 5G. These are nothing but microchannel plate multiplier in 2G. 3G is 3.5 as a photocathode. 4G is actually SHG transparent nickel ferroelectronic, and then 5G is actually 3x5 multi-layer of graphene photocathodes. So these are the technologies which are being developed and where ceramics is helping as becoming a substrate. And ceramics in night vision technology has been extensively used by now in the what I should say security systems throughout the world, and there people are using this kind of wearable dress where the terrorist cannot see you, but you are able to see him. So with this, I thought that let me give a glimpse of the whole thing by telling you that these are the possibilities which ceramics is being given and ceramics is giving. And I think in our country also some of the laboratories are working in these areas and very successful. Some commercialization have also been done, some patents have been made. And as I told you that the market has already crossed 100 billion US dollar, but which is a far reaching object, and then we need to go a long way. And thank you very much for your patience and for your allowing me to speak in this forum. Thank you.
Thank you, sir.
Thank you, sir. Thank you for your speech. Sir have actually discussed about the different possibilities of ceramic materials in our country, as well as the necessity of the manufacturing units to grow in our country. So, sir, thank you very much again. So, the attendees, do you have any questions? So, if you have any question, kindly ask us in the question and answer section. So, moving towards our next speaker. Our next speaker is Dr. Porlash Kumar Haldar. So Dr. Haldar will deliver the talk on generation of transition metal iron doped zinc aluminate advanced ceramics. Sir, over to you.
Thank you, Kunal. Now I'm sharing my screen first. Yeah. Well, my screen is shared.
Yeah.
Yes, sir, it is visible,
Yes,
sir.
sir.
Okay. Thank you. It's now full screen. Yeah. Good evening, everyone. And firstly, let me wish you all a very happy and a healthy new year. And many thanks to Professor Padia, DC sir, and Dr. Chatterjee, who has made a very nice introduction and explained elaborately various aspects of advanced ceramics. So, so that I can directly enter to my topics. Yes, the development of zinc aluminate ceramics. We know that zinc aluminate is a well-known advanced ceramic material with a wide range of applications. In the present investigation, we synthesized and characterized zinc aluminate doped with titania and zirconia separately and studied the properties. And end of the study, we'll see how the improved properties of the zinc aluminate finds a suitability in broader and newer areas of applications. So this is the outline of the contents of the presentation. Firstly, let's have a brief review of zinc aluminate spinel, especially in terms of its structure, synthesis, and application. You know that zinc aluminate is a normal kind of spinel like magnesium aluminate with molar ratio of zinc oxide and alumina 1:1. This is the cubical structure. And right-hand column shows the various properties of the zinc aluminate compound, like mechanical properties, thermal properties, dielectric, optical, and other physiochemical properties. And it has the molecular weight at 183 with a melting point 1900 degrees centigrade. So let's have a comparative study about available various aluminate compounds like magnesium aluminate. Needless to say, to explain about magnesium aluminate, because ceramic people, all ceramic people know about magnesium aluminate very well, and cobalt aluminate and nickel aluminate. And quite interesting that for all aluminate type spinel compounds, they have a very narrow range of melting. And this is quite obvious that zinc aluminate has a wide ranges of applications. True, its quantum is relatively low compared to other aluminate, like especially magnesium aluminate. So now coming to the synthetic part. Industrially or traditionally, the solid state process is followed at the sintering between zinc oxide and alumina, which is occurred at a relatively higher temperature beyond 1600 degrees centigrade temperature. And in laboratory, there are so many processes are available. Out of them, co-precipitation and solid gel techniques are the most popular. Now coming to the application part, this is quite important. We know that zinc aluminate is a wide band gap material, right? So one side it is wide band gap material, and another side this is a spinel and with high volume stability, high inertness, high chemical stability, and also lower surface acidity. This synergy or combination of unique properties has made it multi-directional application. First of all, structurally, if we see that it can be well used, not can be, but it is being used, a catalyst and catalyst carrier, which are used in especially organic conversion and organic synthesis. Here, I just put few examples like dehydration of saturated alcohol to olefin alkylation. These are just few examples only. Second thing, coating material, optical coating. This is used at anti-reflectors coating material in solar cell. Not only for optical, but also presently zinc aluminate is being used as a substitute of even costlier zinc oxide and mixing with special kind of cement, which makes the fluorescent property when it is painted on the wall. This is already being used. So each function is also coating material and paint material, we can say. And lastly, this is the use of semiconductor and sensor, which Dr. Chatterjee already mentioned. While if we see the percentage of the uses of the or application of the zinc aluminate, more than 70% is used as sensor and semiconducting application due to especially having its wide band gap. And out of 70%, 80% used in military and security purpose. I'm coming later in the subsequent slides how it is being used and what's the basic mechanism and how these properties can be improved and how and what is the findings in our present investigation. So now let's have a look at the key concerns of the existing processes of zinc aluminate systems. So I'd say that this traditional or industrial method, which is following the solid state route, which needs the high temperature beyond 1600 degrees centigrade, it itself a drawback. We have to improve because it leads to a lack of homogeneity, non-stoichiometry, crystallographic variation, less flexibility, less uniformity in microstructural feature. So we have to overcome. This is one of the most important thing. And in our present investigation, basically, we studied the effect of tritinia and zirconia separately in zinc aluminate matrix on the densification, structural, optical, and electrical properties. And regarding this, 2 points are noted. So we followed the co-precipitated route for the preparation of the precursor powder, where we restricted the concentration of its dopant up to 2% in order to avoid the adverse effect in the matrix. So now coming to the batch composition, yeah, 2 separate groups were studied, one zirconia doped and one titanium doped, right? And for each group, there are 3 batches, 0.5, 1, and 2. This is basically weight by weight replacement and a dopant addition. So 0.5 dopant replacement of zirconia is coded as 0.5J, 1 is 1J, and 2 is 2J. Similarly, titanium T, right? So total in 7 batches, including the undoped version. So this is the schematics of the preparation of doped and undoped hydroxide gel powder. We already mentioned that we followed the co-precipitation route where aqueous system. We choose the aqueous system, and in order to maintain the basic media, we used 1:1 ammonia with triethylamine, and the pH was maintained at 8.5. So in these experimentations, we used the aluminum nitrate nonahydrate and zinc nitrate hexahydrate ER grade with purity above 99%. And for zirconia doping, we used zirconium oxychloride, and for titanium, we used titanium tetrachloride, right? But titanium tetrachloride, yes, one point is noted that titanium tetrachloride is a bit explosive in nature, but in order to avoid agglomeration in aqueous medium in this experimentation, we purposefully used titanium chloride, but it can be easily substituted by other available material. Yes. So now directly coming to schematics of the characterization of the fired compact. Yes, before firing, we made this green compact, and green compact was fired at different temperature, 1250, 13 and 1350 and 1400. And out of this 4, we selected, here we presented only 1350 degree because of optical property. I'm coming to subsequent slides, but major properties which we studied, the electrical one, and we of course under physical the thermomechanical and densification to compare the effect of the dopant with the existing base material, which was correlated with microstructure and phase assemblage. So coming to now in the first stage, the characterization and analysis of the co-precipitated gel powder. Right. So there are various characterization technique we use. This is a well-known common. The Xrd, XRF, TG, FTR, Xrd SM is scanning electron microscopy and pulsar distribution. Okay, now coming one by one. First, this is basically the physical properties of zinc hydroxide powder dried at 110 degrees centigrade. The first table, the left-hand side shows the XRF analysis, and the second one basically shows the preliminary powder characteristics, and it was quite interesting that with increasing the dopant concentration for both titanium and zirconia, so a specific surface area gradually increases from 128 meters square per gram to 146 for zirconia, and for titanium is a bit higher, 163, which clearly reflects to their particle size by D50. And this is obvious that due to formation of titanium hydroxide and zirconium hydroxide, which are quite fine, which makes this surface area improved and higher, and of course, which reduce the average particle size. Now coming to the thermal behavior of the gel powder, here I consider means presented only 3 analogs. So a undoped version and highest version, that is the 2%, 2T and 2Z. The intermediate version I didn't display here because 2T or 2Z will represent the other things. So now if we see the thermal behavior from the easy thermogravitic analysis and differential thermal analysis, there is 2 endothermic peak centered at around 100 degree and 220, which is basically the removal of internal water from the gel structure and the external and the expulsion of the structural water. And most important thing that there is an exothermic peak centered around 400 degrees centigrade, which is related to the formation of gamma alumina kind of spinel, and especially for 2T, that is the 2% doped titanium and 2% doped zirconia, there is a broad peak centered around 700 degrees centigrade, which correlates basically a higher crystallinity of zinc calibrated spinel, which is evidenced from other studies like FTIR and XRD coming later. So now This is the APR study. The Fourier transform infinite spectra. Yeah, this is recorded of undoped 2T and 2Z batches and of the heat treated version at 400 degrees centigrade, 600 degrees centigrade, and 1000 degrees centigrade. And our main objective to see that at what temperature, which kind of bond formation and occurs. So it is very clear that from 400 to 4000 centimeter inverse is the normal band width of the wave number is selected. So at the higher band wave number, there is an absorption peak, especially at low dried sample at 110 degrees centigrade, centered at 3400 centimeter inverse, and with increasing the temperature, which was basically due to the stretching vibration of wound wedge hydroxyl, and there is also an intense absorption peak centered around 1380 centimeter inverse, we can say, which is due to aluminum double bond O bond, which gradually diminishes with increasing temperature. And with increasing temperature, we see that, especially 1000 degrees centigrade, there is a very intense absorption peaks between 500 to 700 centimeter inverse, which essentially indicates the bond of ZnOAl, which directly and indirectly shows that there is a formation of zinc aluminate at this temperature, lower temperature. Similarly, this is for zirconia. It's the same thing, but here for Zr wedge stretching vibration, which match and basically be overlap between the range 800 to 500 centimeter inverse. So it is not clear, but ultimately 1000 degrees centigrade temperature, this is a well bond is Zn or strong bond is formed, and same evidence also from titanium based matrix. So now, coming to the Xrd analysis, the phase analysis of the precursor powder. Similarly, we took the sample, heated at 110 degrees centigrade, 400 degrees centigrade, 600 degrees centigrade, 1000 degrees centigrade, and three components mainly here. And quite interesting that at the lower temperature, especially 110 degrees centigrade, there is two peaks. These peaks centered around 2 theta, 12.7 and 19.3. These peaks correlates to the formation of zinc aluminum layer double hydroxide. And with increasing temperature from 400 degrees centigrade, there is peaks basically evolved, centered at 30. It's a diffused one, however, 36 and 45. This corresponds to the formation of zinc aluminum spinel, and with increasing temperature, the peaks are intensive, sharpness increases, and at 1000 degrees centigrade, this is the sharpness is the maximum among these four temperatures. This is quite obvious. And if we see the zirconia dope analog, the same one, zinc aluminum layer double hydroxide is formed at the lower, which is found at heat treated sample, and with increasing, this is also diminished. But here, at 1000 degrees centigrade, there is a peak of zirconia, which is isolated. This is a tetragonal zirconia. Sorry, here is another very small peak, which is not shown, around 34 to 35, very small. This is also the secondary peak of tetragonal zirconia. And if we see that titanium analog, the same thing. There, at higher temperatures, at 1000 degree, there is a formation of rutile. So it's quite clear that for higher dopant concentration, say 2%, 2T, especially 2T, there is a secondary phase of zirconia for zirconia doped batch, and for titanium for titanium doped batch is found. And finally, they made a very good composite with mother zinc aluminate matrix. So I will come in, this will be displayed in subsequent slide. Now, if we see the microstructure of undoped zinc aluminate hydroxide gel, Left hand side, you see the heat treated at 110 degree, and the right hand one is the 400 degree. Yes, due to policies at high temperature, obviously the particle size will be higher. And if we see the zirconia part, this is the titanium, and it is quite clear that the particle size is increased with zirconia and titanium doped hydroxide matrix, which perhaps due to, of course, due to agglomeration of the particle. This is needless to explain. This is quite clear. Now, if we say the pore size, the pattern of pore size distribution for undoped and doped counterpart, we see that for undoped part, 30% of the pore lie from 0.5 nanometer to 2.5 nanometer. Here, the x-axis is angstrom. We convert into nanometer, so it comes to 0.5 to 2.5 nanometer lies within 30% of the total volume, and 12 to 18 nanometer lie with 70%. If we see, sorry, just one second. Null.
Hello.
Yes, sir.
I'm not able to shift my slide. There is some issues.
Sir, kindly.
You may reshare it, sir.
Sorry?
Sir, you may reshare it, sir. You can
Oh,
stop and reshare it.
okay. Yes, sorry. I'm stopping it and I'm resharing. Yeah. Thank you. So this is the zirconia. This is for zirconia. You see that the 0.5 nanometer to 2.5 nanometer is 55%, and 4 to 16 nanometer is 45%. Similarly for titanium. So this is essentially means that for 2T and 2Z samples, due to formation of titanium hydroxide and zirconium hydroxide, which helps to reduce to narrower pore size distribution of this zirconia and titanium doped matrix. This is quite good sign. Now, coming to the densification and structural property of sintered matrix. I already mentioned that optimum property of the zinc aluminate compacts observed at 1350 degrees centigrade. So here we consider only this one temperature, not we not display the other temperatures. So this is the table of physical properties of zinc aluminate compacts. Here we see the linear fire shrinkage, bulk density, porosity, CCS, flexural strength, and residual strength for both titanium and zirconia group. And it is quite interesting that sinter density reaches up to almost 96% of the theoretical for both zirconia and titanium. The theoretical density of zinc aluminate is 4.63 gram per cc, and for undoped, we achieved 94%. So it indicates the better sinterability of the spill in presence of the dopant. Now, there are other properties like CCS, cold crush strength, flexural strength, and residual strength. For zirconia, with increasing the dopant concentration, it gradually increases. Just one point, I have to mention, this CCS value or flexural strength residual value, this is not the absolute one. This is just for comparative study. So you may not find the exact value of the CCS, which as per ASTM standard or standard protocol, if it is measured, definitely this value will be much higher. But our actual intention is to compare the properties in presence of dopant, and we are using this co-precipitated gel. Our volume is very low. Our major concentration in this investigation is other properties, especially electric and optical and microstructure and phase assembly. But yes, just comparative purpose we put here. And if you see that the flexural strength for zirconia analog gradually increases with the dopant concentration, this is very obvious that due to formation of tetragonal zirconia and the stress drafting. So one under stress, so zirconia is very common. So tetragonal to monocrete transformation, which resists the further crack propagation and improves the structural properties for zirconia analog. But in case of titanium, this is completely reversed, because we know that there is a little chance of glassy phase in formation with increasing zirconia titanium content. So titanium is completely reversed. With this flexural strength, residual is not very attractive. So structural purpose or structural application, better zirconia, but it is not that titanium can be also used. Titanium can be also used. This is enough for this application. So next, coming to the Xrd study of the zirconia doped zinc aluminum spinel at 1350 degrees centigrade. So it is very clear that from dopant concentration 1 and above, basically there is found the secondary phase of tetragonal zirconia, and the peak gradually is very small for 1, but for 2 this is the more the peak is more clear and more sharper. So similar thing is that titanium for rutile, which basically we observed for 1000 degrees centigrade when the gel powder was heated. The similar kind of observation we got. So after this Xrd study, we are coming to the microstructural study. Here, this is the zirconia doped spinel, zinc aluminum spinel microstructure have been displayed. So extreme left with the undoped, that 0.5, 1%, and 2%. This is very clear that with increasing the dopant concentration, the grain size distribution gradually increases, especially up to 1% zirconia concentration, and after that there is something different. So after up to 1% zirconia dopant is, yes, this looking is orderly maintained. And if we see the titanium, this is again with increasing the titanium concentration, the grain and growth and its distribution gradually increases. And especially for titanium, you see that if we clinically see that up to 0.5% is regularity maintained, but from 1% there is some abnormality started, and yeah, for 2% is for both 2Z and 2T completely different for 2% analog. But it is very clear that for zirconia dopant up to 1% and for titanium up to 0.5% is very regular. And yeah, same micrograph of zinc aluminum center, it is revealed that grain size distribution, if we see the size, that it increases from 0.2 to 1 micron for undoped, and for zirconia 0.4 to 1, so for titanium 0.4 to 1, 1.8, and for zirconia DT 0.2 to 1.6. So after the microstructure study, apparently this is quite apparent. This is not actually apparent. This is the actual thing which we'll like to explain later. So both titania and zirconia are acting in zinc aluminate matrix as a moderate grain growth accelerator, right? So this is the ultimate effect of the addition of the dopant. Now, after the physical study of the center compact, I'm coming on the important, interesting, which is more relevant to zinc aluminate. This is the dielectric and optical properties of the sintered zinc aluminate sphere, which Dr. Chatterjee already explained elaborately and various applications and various aspects. Yeah, for specific zinc aluminate, we have studied these properties like dielectric constant studies, loss factor, AC conductivity, and optical properties. Let's see what happens with increasing the dopant concentration and varying the parameters, and how it can switch the application in broader scope or into new kind of areas. First of all, dielectric constant. Here, dielectric constant is measured with the frequency, of course, and we selected the moderate range of frequency, so 100 kilohertz to 3 megahertz, we can say, and we did the log version. This is the conventional practice, and we see that for titania, we are having the dielectric constant 17, and for zirconia, we are having 15. And we have the standard value, theoretical value of dielectric constant of pure zinc aluminate spinel is 10.6. So more than 50% dielectric constant is increased after the treatment with after addition of the dopant. And for titania, 0.5% gives the best result, and for zirconia, 1% gives the best result. Just recall, in the previous slide, we saw the microstructure 0.5 T, that is the 0.5% titania and 1% zirconia. The structure is very well fit with this observation of the dielectric constant, trend of the dielectric constant. And just one point to add, that the dielectric constant ranging from 10 to, specifically ranging to 10 to 20, and loss factor 0.01 to 0.02 are very suitable material for microwave, especially lower end, of course, microwave application. And already it's going to happen, already it's commercially produced, but only using the zinc aluminate pure, but not doped like titanium and zirconia. Might be some different kind of dopant. So second observation, yes, coming to dielectric loss, which is 10 delta. This is again plotted against the log frequency, and we see that for 0.5 T, again is showing the 0.015 loss, dielectric loss. And the standard loss is 0.0182, which is marginally low, but this is enough for microwave application. And we see that there is a drop of the, or minimum of this dielectric loss around 2.5 megahertz. This is basically interfacial polarization, which is the common for this spinel kind of and this kind of dielectric material. And average loss factor is zirconia, I said, little bit lower than titanium due to a higher grain resistivity. So the unique combination, two things are very important: the dielectric loss, not only the capacitance or dielectric constant, but loss is also an important. The inverse of the loss is basically the quality factor, right? So these properties are very important to design microwave element, microwave compound. And if we see the AC conductivity, which is basically derived from, we can use the basic formula. We know that AC conductivity is 2 pi F 10 delta into the permeability. So this is quite obvious, that which increases with increasing the frequency, of course, which is quite obvious. So we know that with increasing frequency, there is a tendency of hopping of electrons as again boundary, and it's a mechanism, this quantum mechanical tunneling at the high frequency. So zinc OAL, this is a bond, so electron transfer from zinc via oxygen to aluminium. So it is a kind of quantum mechanical which is influenced, especially even high temperature and high frequency. So we see that with increasing the frequency, AC conductivity is also increased. And lastly, coming to the optical property, yes, we also measured the optical property of titanium doped. Of course, we measured zirconia, but I displayed the titanium. This is the more important, but a more interesting and promising. Titanium doped zinc aluminate spinel. This is the very familiar top plot. Y-axis is the alpha is nu. Alpha is the molar absorption coefficient, and x-axis this is the energy we absorbed is nu. So where this line, if we increase the line, which intersects the x-axis, this will be the band gap energy. So here we found that with increasing the dopant concentration, the band gap energy reduces from 3.8, 3.8 the standard, and we also achieved this almost standard value 3.8 electron volt, and it is reduced up to 3.48 or 3.48. This is very, very important thing, because this range 3.48, 4 to 3.5, this is the band gap of gallium nitride. Gallium nitride is being used in various, enormously used in semiconductor field. So we are also getting with titanium doping similar kind of band gap energy. It is 3.49. So this is quite significant, and we can say that the zinc for titanium doped zinc aluminum spin, there is a direct allowed band gap. Yes, from the formula, it's quite obvious that alpha is nu is 0.5, and R is 1.5. This is the notation of direct allowed process, of course. And with increasing the titania dopant, there is a tendency of grain growth. So with increasing grain growth, the resistivity gradually decreases, and which helps the optical transparency of the system. But this, not only from microstructure, this is also a material property, of course. So unique combination of the material property, the titanium doped zinc aluminate, along with this microstructure, especially 2%. Even we didn't start. We don't know what will happen in 3% dopant addition. But yes, using 2% dopant, we are having a very promising band gap value. So 3.49. So I'm coming. It's interesting application how we can apply in our practical field. So after this study, there are basically three major parts of intervention we can conclude. One, synthesis part, second, property, and third, application. So if we see the application, synthesis. So it is clear that this both doped and undoped version split with titanium and zirconia, so doped. This can be effectively synthesized through aqueous phase co-precipitation route, maintaining the pH. Of course, if somebody says that why not solvent process, we know that solvent process will give relatively better properties, but it's low. If we optimize the entire process from ultimately we have to correlate the property and cost effectiveness, availability, everything. So co-precipitation method, I would say that this is more optimum process. This is a relatively lower cost effective, and of course lower cost. Sorry, it associated lower cost and properties are also optimum. So from synthesis aspect, one point can be concluded. Now, from property point of view, we say that the 0.5%, better to say that, yeah, the presence of dopant up to 1%, you can say, basically exhibits the well crystalline zinc aluminate phase, along with a small dispersion of titanium zirconia at secondary phase, leading to generation of dates, zinc aluminate metal oxide composite. And if we clinically analyze that, for the titanium 0.5% and for the zirconia 1%, and if we see from Hegar's law from solid solubility, so it is very clear that 0.5% weight percent stock, this is well make the solid solubility limit, but up to 1% for zirconia and up to 0.5% titanium might be a very good option to choose for further applications. And if we see the next part, the application part, so essentially the zirconia has the more inclination towards the structural property, which covers the entire catalyst and catalyst support, basically structural component, and of course coating part. And for electronic applications, especially semiconducting part, with band gap, required band gap property. So titania is the major inclination. So after this study, as way forward, I would say that both of these can be used as a novel catalyst, and of course, yeah, we have to test that how this improved property can match with this catalytic behavior, because titania, zirconia, when this is producing the secondary phase and composite, and these are transition metal element, definitely there is a chance of higher functionality as catalyst and catalyst carrier. So this is one point. This is a structural point of view. Now the second point, of course, we are having the dielectric constant higher than the existing theoretical value. So how to it can be used in microwave application in broader area. Thirdly, it can be also used the specific kind of LED and semicon laser application, of course. Number 4, in multi-junction solar cell for efficient power conversion. This is one of the most important things, because most of the solar cell are silicon chips based. Most of them, of course, there are which are single junction, basically junction route. They follow the single junction route. There is some drawback also, because as far SQ limit, Shockley-Quasi limit, we know that for the solar application, 1.5 electron volt band gap is the optimum, we considering the all aspect, which if we translate into the corresponding the wavelength or frequency, this is considered lower end, lower frequency and higher wavelength region. But the intermediate frequencies or intermediate wavelengths are not effectively absorbed by solar cell when we are using silicon. And with silicon chips, we are presently using cadmium telluride, which is also environmentally is not, yeah, you know very well, cadmium is still, both are hazardous. And its maximum efficiency or solar power conversion to electric power conversion is theoretically 33. We can say that practically 30 is reaches, but rest 70% is wasted. Wasted means we are not, this is not able to absorb. But if we use the wide band gap material like gallium nitride, yes, gallium nitride, which are costly, very, very costly. So this multi-junctional, using this multi-junctional component, then this power conversion efficiency will automatically grow to 80%. So huge jump, but the cost is very high. But now, if we replace zinc, titania doped zinc aluminate in place of gallium nitride, costly, you know very well, gallium nitride is very, very costly. So let's see what's its application and how. Definitely, I believe that because the major property is the band gap. So if the band gap energy for gallium nitride and titanium doped zinc is the same on similar band, so it can be effectively also used in this application. After that, I am coming also electric hybrid car, and where multi-junction point is very, very important, and gallium nitride is again used because there is no substitute. Because silicon carbide, this is also costly. Semiconducting grade silicon carbide also costly. If you use aluminum nitride, you know very well aluminum nitride is not very stable because there are huge cost of production and also the storage purpose. But if gradually we substitute using this stable spinel type compound like zinc aluminate doped with titanium, so cost will be also reduced without any, and durability also high, and without compromising the quality. This is one of the most important thing. Next point, due to having higher wide band gap material, higher electric, with these have higher electric breakdown field. There is a low band gap energy like gallium arsenide, silicon chips. There is limitations because if there is a huge voltage fluctuation, if there is very high temperature, if there is a high frequency, they are not able to, because you know very well, with increasing this parameter, the valence bond, valence orbital and conducting orbital distance will be very overlapped, and this will damage the system. This will burn out. So at higher temperature, especially beyond 300 degrees centigrade, even 500 degrees centigrade, what the very critical environment, that this silicon based or gallium arsenide based semiconductor are not functional. So there definitely we have to opt the wide bandgap energy, or wide bandgap material, like which is very common in gallium nitride and special type of silicon carbide. But again, there are some limitations. These are high cost, yeah. So and of course lower durability. So now this has also the potential application in this field, where this doped zinc element can substitute this costlier material. This is both energetically and also environmentally, of course, cost. This will be more favorable. So finally, just I would like to mention that this titanium doped or zirconia doped, we can't say that this is a completely new kind of material, because we know titanium, we know zirconia, we know zinc and zinc aluminum material. This is common. But I believe that the present investigation, but present findings will bring a massive change in the field of in the field of applications, and opens new lines of research followed by industrial practices. That I believe. That's it from my side. These are the list of publication, and yeah. Thank you.
Thank you, sir. Thank you for your very detailed speech on your particular topic. So I think we don't have any question right now. So, sir, we will move towards our next speaker. So our next speaker is Dr. Shobik Dey, who is the Senior Manager at Tata Consulting Engineers Limited. Dr. Dey will deliver on the topic generation of noble muellite and its composites based on bauxite and fly ash. Sir, over to you.
Yeah, my screen is visible.
Yes, sir. Yes, sir.
Yeah. Good evening to the Honorable Vice Chancellor of Maulana Abul Kalam Azad University of Technology, Professor Soikat Maitra, the Director of School of Energy and Environmental Science, Makaut, Professor Dr. Tapun Kumar Padia, Academic Advisor, Professor Vibhuti Bhushan Paira, Professor Anand Kumar Das, Department of Environmental Science, and Mr. Kunal Chaudhuri, and to all other distinguished speakers, Dr. Arup Kumar Chattopadhyay and Dr. Palas Kumar Haldar, who are eminent in their respective field, along with all my fellow participants. It is my privilege to be here, and I take this opportunity to express with prodigious pleasure my heartfelt honor, profound gratitude to the Honorable Vice Chancellor and Professor Padia to give me a chance to deliver through the webinar platform organized by an university of repute. The topic I will deliver is generation of noble muellite and its composite based on bauxite and fly ash. During my delivery, first I'll throw some light on the recent trend of muellite. I'll brief on the available literature till date, along with the phase diagram, aluminum silica phase system and muellite structure. I will also explicate the work plan and what are the experimental procedures I have undertaken during the study and the results obtained. Finally, I will draw the conclusion, and last but not the least, whatever the futuristic scope of the study I will mention. Now coming to the introduction part, normally the recent trends, stoichiometric muellite and muellite-based composite ceramics have been emerging as a potential candidate for advanced structural and functional ceramics for their widespread applications as multifunctional materials. The technical importance of Mueller ceramics is evolved from its inherent properties like low thermal conductivity, outstanding thermal stability, low thermal expansion, and not but the least, the good mechanical strength even after exposure to the severe atmospheric conditions. Now, there are two forms of synthesis routes. The first one is through conventional mechanism by using clay minerals, aluminosilicates, or by clay alumina or clay bauxite having relatively coarse particles. And the second one is non-conventional technique. Each mechanism has their pros and cons. In conventional process, the processing temperature is energy and intensive, but in non-conventional technique, the muellite form are not outstanding of outstanding properties as good as the muellite form in the non-conventional technique. But however, muellite derived from high purity precursor, that is in the non-conventional route, is quite expensive and not a viable option, for its large scale production due to low yield and complex processing techniques. In this study, a novel, innovative, holistic, and cost-effective approach has been established by synthesizing stoichiometric muellite having desirable properties by reaction sintering of high aluminous rock fly ash in presence of the prospective sintering aids. Now, coming to the what are the things I'm covering. First, I'll brief about the whatever the recent things of the muellites, basically the basic information of the muellite, a glimpse of the synthesis of the muellite, effect of the sintering additives, what are the effects on the some kind of prospective sintering aids, their properties and the applications. So this is basically the silica alumina phase diagram. According to Aramaki and Rustom Roy, muellite melted congruently, that is muellite melted directly to a liquid whose composition remained constant with an increase in temperature. A silica muellite, you take the temperature at 1595 degrees centigrade, and a muellite aluminum you take the temperature at 1840 degrees centigrade were observed. Later, the Klug and et al. Proposed another silica alumina binary phase diagram wherein incongruent melting of muellite at 1890 degrees centigrade and shift of both boundaries of the muellite solution region towards higher alumina content is observed. Basically, the primary muellite, that is M1 muellite, with is some kind of cuboidal shape. Basically, it's a rod-like morphology, was derived by decomposition of the spinel type structure of metakaolin and the residual amorphous silica reacted with alumina, producing secondary muellite. Secondary muellite form from a major solution precipitation process via a transitory liquid process, and the third kind of muellite, that is M3 muellite, is formed due to the presence of dopant facilitating nutrients for the growth of these muellite seeds, which give based on their crystallization habit. This is the typical muellite structure. The structure is basically orthorhombic. It's an analogous structure with the sillimanite is the space group is PBANM, and the crystal structure of muellite is PBAM. The backbone of the structure is sillimanite and muellite as edge sharing of AlO6 octahedra, forming chains running parallel to the C-axis. The octahedral chains in sillimanite is linked by the tetrahedral T2O5 group. T2O5 group is basically T represents either Al plus 3 or Si plus 4. Basically, in the muellite part, some of the Si4 plus ion is replaced by the Al3 plus ions, and that is why some compensation is some compensation deficiencies happened in the structure, and this compensation of the substitution induced charge deficiency is achieved by the removal of the several oxygen atom from displacement of the T position to the next T star position, and that forms a di-cluster groups, T2O5 groups, which links with the oxygen atoms. These are the basic properties and compared with the other structure of the muellite properties. In the muellite properties,
Hello, Dr. Day, sir, your voice is not coming. Hello.
Sir is facing some internet problem. Let us wait for a few seconds.
Okay, okay.
Hello. Let's proceed.
So maybe sir has been disconnected due to some internet problem.
Please restore.
Kunal sir, please, if you can talk to sir.
Professor Pariya, sir.
Hello. Follow.
Sir, if you can contact Dr. Day, sir. I think he has some technical problem or network problem, I think.
I will talk to him.
Yes, sir. Dear attendees, please stay tuned. The problem will be actually sorted very soon.
Sir is back with us.
Sorry, I got disconnected.
Yes, sir.
Yeah. Please proceed.
Yes. So what I'll do, sir, I will share my screen only, sir.
Yeah.
Yeah. Coming back to the synthesis of muellite, basically based on the different starting material, a variety of muellite ceramic processing routes have been developed. This includes solid state derived muellite, liquid state derived muellite, sol gel derived muellite, cytothermally produced muellite, gas phase delivered muellite, spray pyrolysis approach, and processing with other miscellaneous method. Muellite synthesized by liquid and solid state method are designed as fused muellite and sintered muellite respectively, while the other methods are referenced as chemical muellite. Now these are the dopants steel that used in the while preparing the muellite, and they are whatever their brief characteristics of the sintered muellite produce, like ECl, lanthanum, cerium oxide, B2O3, cobalt oxide, gadolinium oxide, etc. Why this study has been undertaken? There are few objectives. The first one, there are some investigation regarding synthesis of muellite ceramics has been carried out exclusively either from fly ash or from bauxite, but no such exclusive in-depth research in the alumina region of the silica alumina binary system by using fly ash and bauxite in presence of prospective sintering it and such as sintering bohemite has been carried out. Number two, the temperature of processing is very high in the reaction sintering process. So with an intention, with an aim, we have to reduce the temperature. And the process is how we have to add some prospective sintering aids with an optimum content. The third one, in order to achieve good quality muellite, by solid state sintering, we have to use we have to achieve the optimum properties by smaller particle size. The fourth one, it's a cost effective. The fifth one, it's an effective utilization of naturally occurring abundant materials. The sixth is a environmental friendly because we are using the fly ash. So lot of fly ash are used in the India. Almost 250 million fly ash is produced per annum in India. So out of 250 million of the fly ash, 78% fly ash is used, but today's 22 fly ash is dumped. Whether I don't know whether it is maintaining the environmental norms. So if we use this out of 22% of this fly ash, so if we use at least 0.5 or 1% of this fly ash to produce this material, it will helpful, and it should be environmental friendly. Now, coming to the how the procedure has been taken, how the plan of the work. These are the batch has been selected. Like the batch 1 is without additive. Batch 2A to 2E is the bohemite percentage varying from 0.2 to 1.5%. Yttria. Batch 3A to 3E, and the last batch is batch 4A. It consists of 0.75% yttria and 0.75% bohemite. These are the oxide composition derived either from the Mueller precursor without additive, in presence of bohemite, in presence of yttria, and the combined additive. This is the schematics for preparation of Mueller precursor. Now this is the procedure how the precursor powder has been produced. Now the complex, how the complex has been prepared. Like precursor powder, initially it has been calcined at 600 degrees centigrade for 2 hours. It has been sieved, mixed in a high mix at an alternate mixer, then hydraulically pressed, prepared bar, dry it, and then soaking time is fired it at from 1400 centigrade to 1575 degrees centigrade with a soaking time of 4 hours. These are the experimental procedure undertaken for the raw materials as well as the Mueller precursor powder what has been produced. This is the experimental procedure carried out for the fired compacts, thermomechanical phase analysis, microstructural. Now coming to the results and discussion portions. First is the source of oxide raw material characterization. Chemical analysis of the bauxite reveals that the alumina is the main constituent with minor presence of silica and iron oxide. Typical loss on ignition value of source of bauxite indicates that the gypsitic kind of bauxite. The high value of LOI is attributed to the presence of both interlayer and hydrated water. The TGDTA graph of natural source of bauxite shows the presence of a sharp endothermic peak at 300 degrees centigrade because of the dehydration of hydrated alumina by the expulsion of adsorbed and interlayer water, leading to initial transformation into disordered bohemite phase. The FTR spectra also reveals that bands at 3695, 3621, and 3522 correspond to stretching vibration of the interlayer hydrogen bonded OH groups, with spectra at 3452 and 3379 are assigned to the stretching vibration of interlayer hydrogen bonded OH group. The powder Xrd pattern of natural bauxite sample confirms the presence of gypsite and bohemite as the major mineral phase, along with few amount of quartz and anatase has minor phase. Same micrograph of the bauxite sample reveals a microstructure with elongated grain size distribution in the nano range of 102 to 250 nanometer. Chemical analysis of the fly ash also reveals the presence of high percentage of both silica and alumina with low content of iron oxide, lime, and magnesia. The analysis confirms that impurities are within the reasonable limits and will not badly affect the properties of derived reaction sintered muellite compacts. The particle size distribution analysis demonstrated that 70% of the as received fly ash is in the finer than 30 micrometer and the average D50 value is 30.19 micrometer. DTA and TG also curves indicates a very little oil loss through a continuous endothermic reaction. The initial loss is due to the removal of absorbed water in the sample. a major loss is because of the whatever the fly ash unburnt carbon is present in the either in the thermal power plant or in the other plant. This unburnt carbon comes out. The Xrd pattern of fly ash also shows the major phase present are mullite quartz. Some additional weak peaks are due to the presence of hematite and outhite. The sample is also observed to contain magnetite as well as free iodine in small percentage. The same micrograph is also image shows the presence of spherical particles of different size. The particle size lie within the range 0.18 to 590 micrometers. The precipitated silica, it's a the silica percentage 86.55%. It's a purely amorphous in nature. The powder Xrd pattern shows that indicates the material is almost amorphous. The same study illustrates that the amorphous silica particles have almost uniform size distribution, varying from 50 to 70 nanometer. These primary particles have the tendency to agglomerate, leading to strong from large particle size. This is the characterization of stoichiometric mullite precursor. The texture of the precursor powder and its optical appearance clearly indicates the presence of mixed phase ingredients. The absorption band appears at 700 to 750 centimeter region is assigned to the stretching vibration of AlO6 octahedral units. Now coming to the linear firing sinkage. This is the densification behavior. Basically, the sinkage as such multi-phase precursor is initially due to the removal of structural water from the precursor by elimination of pores, by material transport, the formation of crystalline phases through the interaction of the ingredients, formation of liquid phases from the fluxes, and recrystallization of secondary phases. With progressive rise in temperature, the increase in linear sinkage is noticed due to the simultaneous formation of cristobalite and subsequent interaction of cristobalite with alumina to form primary mullite. Cristobalite formation increases densification, reducing reaction path for aluminum silicon ions, leading to an intensification of mullitization, while increasing bulk density through pore consolidation, pore removal, shrinkage, and finally grain growth. Since active alumina in synthetic boehmite has an inherent tendency to rapidly react with cristobalite to generate mullite even at a temperature of 1550 degrees centigrade and above, thereby enhancing more or less complete annihilation of pores in the sintered compact containing 1.5% boehmite. With the progressive rise in firing temperature and yttria content in the composition, more and more densification occurs with low porosity content because at this stage, enhanced yttrium silicate has been produced, which favors the simultaneous lattice and grain boundary diffusion. However, yttria appears to be less effective than that of boehmite as an additive in the open pore removal of the sintered mullite body in all additions and irrespective of the firing temperatures. Since active alumina synthetic boehmite has a tendency to react with cristobalite to generate mullite at the temperature of 1550 degrees centigrade, it yields high bulk density with the corresponding elimination of the open porosity in sintered compact. The more pronounced influence of boehmite from 1.2 to 1.5% is observed. And with progressive rise in the temperature and with progressive rise in the dopant content, more bulk density is achieved. It is reflected from the picture that from the figure that the in comparison to yttria, boehmite addition results in high bending strength, which may be due to the uniform distribution and also interlocking of the secondary mullite grains throughout the matrix. Since active alumina in synthetic boehmite has a tendency to react with cristobalite readily to generate mullite, even at 1550 degrees centigrade, a remarkably high flexural strength of 78 to 85 megapascal is achieved. All the samples is a thermal shock resistance result sense. So basically, all the samples sintered at different temperatures are subject to 20 cycles of repeated heating and cooling at 1000 degrees centigrade as per the air quenching method. The test result highlights that no microcracks even is observed in each of the samples. So, it is proved that it's a good thermal shock resistance and have a greater thermal stability of the sintered mullite compact. On the retention of relative high temperature, almost all the samples have a retention value of the flexural strength is 60%, And when the bohemite or HF percentage is high, the retention value will also increase, and it's optimized at 69% of the retention value of the original compact. This is the coefficient, coming to the coefficient of linear thermal expansion. Doping of mullite with foreign cations can have a significant influence on thermal expansion. Few doped mullites are known to exhibit a lower thermal expansion than that of pure aluminosilica mullite. The thermal expansion also depends on the amount of glass present and its composition. The impurities in the starting materials may enter into a mullite that is as a dopant, which likely to influence the thermal expansion property of the fired body. Compacts free-form additive, optimum glass content along with the considerable open porosity in the matrix are attributable to low coefficient of expansion. But with increasing temperature, the porosity decreases, increase the coefficient of expansion value. When the alpha alumina or the mullite has been produced, the expansion value is increased because the alpha alumina or mullite has the high coefficient of expansion value. If the porosity is reduced markedly, which is the adverse effect of the coefficient of expansion value in the temperature, high temperature. The COE value initially decreases with the addition of yttria, probably due to the formation of yttria silicate gas. With a further rise in temperature of firing, the coefficient of expansion value increases due to the elimination of porosity and formation of additional crystallogic phase like alpha alumina corundum, having a relatively high coefficient value coefficient of thermal expansion. With the refractory, and this now coming to the refractoriness under load, with the gradual rise in temperature of firing from 1400 degree 50 to 75 degrees centigrade, dissolution of in situ form alumina in the transitory liquid phase leads to the saturation and subsequent reprecipitation of the secondary mullite crystal with interlocking morphology, resulting in moderately high RUL value. With increasing temperature and with increasing the dopant content, the RUL value increases up to 1675 degrees centigrade. In presence of the addition of yttria silicate is to be formed, which dissolves readily into the aluminosilicate glasses, resulting in a decrease in the viscosity of the aluminosilicate glass. This in turn results in a moderate RUL value. However, with the gradual addition of yttria up to 1.5%, the yttria silicate is obviously formed to a large extent by consumption of silica. The yttria silicate in turn leads to precipitation to residual alumina, which is being entrapped within the well-grown mullite grains, leading to dense interlock microstructure and enhancement of its RUL value to 1675 degrees centigrade. Fired at 15, the sample fired at 1575. Now coming to the true density, since mullite possesses lower specific gravity than corundum, with an increase in the alumina content or alpha alumina or corundum in the sintered compacts through the incorporation of bohemite, true density of the sintered body is likely to increase progressively with rise in the temperature. This is the Xrd pattern. Some typical Xrd pattern has been depicted here. Batch 1 sample on firing at 1400 degrees centigrade exhibits primary mullite as a major crystalline phase, but with gradual rise in temperature, cristobalite disappears with mullite formation, which starts mullite formation, and ultimately at high temperature, cristobalite completely disappeared and the mullite phase has been evolved. Similarly, same thing is applicable for the bohemite as well as the yttria addition, but for bohemite, some alpha alumina and corundum crystal has been observed. These are the results for the reed belt analysis. In the reed belt analysis, basically without any additive sintered at 1450 degrees centigrade, the presence of both cristobalite phase of 44.8% is observed, and a predominantly primary mullite phase of 54.5%, 35% 8% is observed. With increase in firing temperature, mullite content continuously rises at the cost of cristobalite. So initially cristobalite forms, but later it has been disappeared and mullite formation starts. Corundum is also formed due to the dissolution of alumina out of the transformation of the alumina, as I have already explained earlier. And alumina secondary mullite as the temperature of firing increases from 1450 to 1575. In situ form alumina with silica to form either primary or secondary mullite also form, and or otherwise dissolution of reactive alumina into transitory alumina silicate liquid phase followed by reprecipitation of secondary mullite is also observed. Presence of corundum is also gradually diminished in the fired body containing 0.4 to 1.5% yttria respectively. In some cases, with addition of yttria silicate is also observed. Now coming to the Redux analysis, the Redux analysis of muellite and muellite-based composite fired at 1450 revealed the peak of aluminum, oxygen, and silicon with a weight percentage of 40.85 to 10.61 and 48.54 respectively. It reveals that the component closely correspond to the individual element like primary muellite. Also, in 1575 degrees centigrade, the peaks, whatever the peaks observed, that it contains the aluminum, oxygen, and silicon, which corroborate the presence of the primary and as well as the secondary muellite throughout the matrix. So we have observed the presence of cristobalite, we have observed the primary muellite, we have observed the secondary muellite. Also, muellite compact containing 1.5% bohemite or 1.5% yttria. The presence of corundum particles is also, elemental corundum particles is also observed. Now coming to the microstructure study. Few cubitical shape primary muellite is observed when the sample is fired at without additive at low temperature. With rise in the temperature, the uniform equiax secondary muellite is observed, which is uniform and homogeneous in nature. And secondary muellite is basically nucleated from the tangerine glassy phase formed by dissolution of in situ alumina from bauxite. With rise in the temperature up to 1575 degrees centigrade, more elongated muellite grains interlock structure is observed. With presence of the dopant, with presence of dopant, some acicular M3 type muellite is observed in the matrix throughout the matrix. Higher percent with addition of higher percent of bohemite, and during firing at 1400 to 1500 degrees centigrade, the M2 type muellite, basically rod-like morphology is observed in the muellite matrix with the aspect ratio along with the few M3 type muellite having longer aspect ratio. Microfine active alumina is also available from bohemite augmented solid state interdiffusion from the muellite sheets. Existence of corundum grain adhered to at the multi-grain junction. So corundum grain, that is basically alpha and is also observed. With increase in percentage of it, when the yttria percentage has been increased, a distribution wider grain size is observed because it's a abnormal grain growth is observed with addition of the yttria. Grain size is comparatively larger than when the presence with absence of any dopant or with the presence of any bohemite. Digital layer of yttria silicate triggers up the mobility of boundaries exhibiting random morphologies. That's why the abnormal grain growth is observed in the curved grain boundaries. With rise in yttria content, yttria silicate is obviously formed to a large extent by consuming silica. Yttria silicate in turn leads to precipitation of excess microfine alumina in the batch, and it is entrapped within the well-grown muellite grains through lowering the alumina silica molar ratio. Now, for the mixed additive, like while we putting that 0.75% bohemite and 0.75% yttria into the matrix, an exceptional properties has been achieved. Desirable phase assemblage along with an uniform dense and homogeneous with the interlock microstructure of muellite based composite has been observed at 1575 degrees centigrade. And this is the optimum scenario. Corundum particles formed and adhere to the grain junction of muellite, favoring diffusion of ions in neck areas and filling up of pores, cause substantial reduction in porosity value, that is 0.05% with high BD. Significant improvement of flexural strength, 99 megapascal, and presence of substantial proportion of muellite, that is 96.2%, and corundum 2.30% free from cristobalite. This is observed. This is the Xrd pattern and the same micrograph of the fired compacts with the mixed additives. Now I will conclude. Basically, this is the sum up scenario. Whatever the composition has been carried out, and the last this batch 4A, we have observed that this is an optimum composition fired at 1575 degrees centigrade with a linear sinkage value of 19.98. Apparent porosity is 0.05, bulk density 2.86, flexural strength is 99, and RUL is 1683, degree centigrade TA value, and true density is 2.94. So, so cost-effective mueller ceramic has been produced because of the it has been produced from the indigenously available raw materials and industrial waste fly ash. Without addition of any dopant, primary mueller is produced and the crystallite preferentially formed, but with rise in temperature, the crystallite disappears and the mueller formation accelerates with rise in the secondary muellers. Boehmite is basically beneficial for formation of the interlocked microstructure with homogeneous morphology, because for this the RUL value as well as the strength and the other desirable properties is very good. Yttria favors a gain growth, but because of the higher percentage of the yttria, throughout the matrix the abnormal gain growth is observed, which may also helps the increase the bending strength. But compared to yttria, the boehmite addition is better, and both dopants addition help in increasing the diffusion rate, facilitating interlocking and distribution. So we have observed that the optimum percentage is better compared to the individual yttria or boehmite additions. This is the futuristic scope. So we have to basically mathematically simulate the results obtained and optimize the additives content. Use of fly ash bauxite from different sources to be checked. I have used Brockesser fly ash and the Source boxes. So the same result to be replicated for addition of the either from different source of the bauxite or different source of the fly ash. The pilot scale of production can be made for blast furnace at application, along with the compare the results obtained with existing refractories. This can be also be used as a high alumina aggregate. The micro hardness, heat capacity determination for catalyst support also can be determined. Also, it can mutate can also be used for the antibacterial properties. And it's also used for the other sintering at joint lips, like we have used the yttria or boehmite. So other sintering it can be added and check the properties and optimize the optimization. Further optimization can be possible. That's from my end, sir.
Thank you, sir. Thank you for your very good and detailed presentation of your topic. So, dear participants, if you have any questions, you can actually ask it in the Q&A section or in the chat box. So, right now we don't have any questions. So we will move towards the next part of the program. So now I would like to request Professor B.B. Poira, Academic Advisor, Makaut, to deliver the valedictory speech of this evening. Sir, over to you.
Sir, please unmute your mic, sir.
I hope I am audible now.
Yes, sir.
Yes, sir.
Professor Dr. Soikat Mitra, Vice Chancellor, Maulana Abul Kalam Azad University of Technology, Dr. Arup Kumar Chattopadhyay, Dr. Tapan Kumar Poria, Mr. Kunal Chaudhuri, two young scientists, Dr. Souvik Dey and Dr. Palash Kumar Haldar, dear participants. It is a great evening, and I was really mesmerized by or taken to a new height by the speeches from the beginning. Kunal introducing, and then Dr. Poira, Tapan Kumar Poira, giving the background and also telling us how ceramics are changing the pattern of utility or improving the devices in electronics and microwave devices. the Vice Chancellor is a great motivator. Apart from throwing light on how artificial intelligence is being useful in all such devices, he suggested, and which he always does, that a web series should be planned with Dr. Arup Chatterjee taking the charge as chairman, where even uh, uh, foreign scientists should be invited to deliver lecture. Now, coming to the topics and the lectures of the two young scientists, Dr. Palas Kumar Haldar and Dr. Souvik De. For both of these topics, they have narrated everything, starting from the raw materials, what the characterization of the new product, the properties, all these things they have thrown light both uh, on zinc aluminate composite and also um, uh, rather manufacture of mullite from bauxite and fly ash and precipitated silica. I have a suggestion to the guy. First of all, I must congratulate Dr. Tapan Kumar Poria for suggesting these two topics to his scholars. I would request him not to stop here, but to continue the work on these two fields, make a study of the gaps which are there at the present moment, and filling up those gaps, making a study on the cost effectiveness of the projects. And I'd request the Honorable Vice Chancellor to have two pilot projects in our university. One for the composite, low zinc aluminate ceramic, and also for the mullite project. So you can take up these two projects in our campus on a pilot plan project, so that these could be commercialized in future. The composite seems to be very much attractive because Dr. Haldar has given a lot of information, bringing down the temperature, increasing or raising the quality, and in some cases, the quality is, if not superior, almost has the same characteristics as of the uh, material used at present. And in the other case, Dr. Souvik De, as he just pointed out, this will have an enormous impact on the environment by utilizing even a small percentage of fly ash, whatever might be, for useful purposes. So what I can suggest to Dr. Poira is to submit a, these two projects for funding agencies for grants, and we can set up these two pilot projects at the Horingata campus. With these remarks, I thank everybody, particularly the Department of Renewable Energy, for organizing this webinar, and look forward to some such webinars, rather web series, to be organized by Orup in near future. Thank you very much.
Thank you very much, sir. So before going towards the end, so we have a question from Manik Chandra Das. So his question is, for common ceramic materials like insulators or pottery items, we see when it breaks, it loses usability. What researches are going on regarding recycling of ceramics from green environment point of view? So, sir, any of you can answer this question?
I can add one thing, that there is now bendable concretes with fiber glass reinforced material. You will have now bendable concretes. You will
Yes,
have
sir.
self-repairing cement with, say, um, uh, microcapsules of epoxy resin. You can have self-repairing cement. So such things will come up. Possibly the Honorable Vice Chancellor may add something on this regard.
Question is what? Recycling of materials, ceramic materials.
Yes,
No,
sir.
no, no. No. This cracking, how to check cracking of porcelain materials? No, that is the question.
How to check?
Hmm.
How to check cracking means how to check or how to prevent? Checking is done by.
Brittleness. How to reduce brittleness?
Okay, how to reduce brittleness? The reduction of brittleness basically is associated with making the materials in the multi-layered forms, where polymers are used
Yes.
as these sandwiched in a sandwich format between the ceramic materials, and it improves this this tensile strength of the ceramic materials, and improves the impact towards this heat and all these things. So these are all this mature technology. Ceramic materials are mixed up with these different sorts of these polymeric materials for improving all these properties. Now, regarding this, there are there's lots of innovations are happening in ceramic materials as well. So one of the innovation is this, particularly in porcelain and all these things, as I was mentioning earlier. People are using these porcelain materials, sanitary wares, all these kitchenwares, and all these things, associated with this digital health aspects of consumers, because this is altogether a different market scenario. Now, when the materials are being designed, the materials are embedded with different sorts of sensors and different sorts of these features, so that at any point of time, if I spit something on this on the this basins, or all my excreta and all these things, so these are going to these sanitary wares and all these things. These are uh, at each and every moment when it is done, then all the information, particularly my body parameters associated to all these things, these are getting captured, analyzed, and all these things, and then this processed. This is AI enabled, these sensor data capturing, sensoring systems, and this is this in particularly modern these homes and all these things, smart homes. This is one of the one of the features, one of the integral features of any modern homes, where people of this advanced age group, who are basically staying without any companions, or without the relatives and relations and all these things. Their all data are taken care by all these sensors and all these wares, and these are being transferred to clouds, and these are going to the medical centers, where this the timely interventions from medical centers can happen at the right point or right moment. So this is one thing. Second is, you see, when we're using ceramic wares, I was just taking coffee with one of my porcelain mugs here. But the problem is, when I was talking, by that time the coffee got cold. So this is one of the problem. Now the smart, these materials, smart cups is like this, which will maintain the temperature so long I am consuming it. So this is one of the aspects. Similarly, for foods and all these things, there are insulators and all these things, but at the same time, there are this many devices available by which the optimal quantity of heat can be retained. This microwave heating. What is the problem of microwave heating? The problem with microwave heating is material at the core of this is of the material gets the maximum amount of heat, and this periphery gets the minimum amount of heat. That's why that leads to confusion. Confusion means if you take or consume one samosa, taking out it from microwave oven, surface is cold, you just give a bite, immediately your tongue will get burned because this inside is very tremendously heated. And that is that is one of the aspects of our health hazards, because our body system is like that. If I take something warm, our body get adjusted to it and then help it in swallowing. But suddenly, if there is a change in the signals and all these things, the body systems get doesn't become accustomed to it, and it may lead to cancer. So this is one of the biggest problem of microwave heating of food materials. But when we are keeping it in ceramic items, now the research is going on, the ceramic items then try to distribute this temperature inside the food item in such a manner that each and every moment you will get uniform heat from the surface of this, of the heap of the food or stack of the foods to the core of it. So these are all these latest innovations, and these are happening at many places. So taking care of these foods which are conducive for our health, taking care of our health and all these things, these are very much this one of the important applications of ceramic materials for the future generation. But the novel thing of ceramic materials, particularly this is happening in the field of glass, because anything as a computer, future is like this. Anything as a computer means all these wall panels, your tabletops, all these things will be a computer in near future. Anywhere you just place your hand, this immediately based on your fingers, these images and all these things that gets that wall will be activated and will start, this interacting with you. These interactive wall panels or computers, all these things, these are, this it's a reality, and it is possible because of this advancement, these glasses and all this, this glass and all these composite materials like this, which are part of the building materials. Buildings of the future will contain lots of construction materials in such a way that this will help you to pass on information or to receive information, number one. Number two, to take care of your health. Number three, there are, this in concrete also, the concept is now translucent concrete. Putting fiber optics and all these things inside the concrete, people are making this concrete, the semi-transparent or translucent, which gives you, more expansive feeling inside a room. Yeah, you can see my wall of my room. This is absolutely opaque. So it is giving some sort of claustrophobic syndrome. But when if it is either transparent or semi-transparent, it gives rise to openness. This openness, feelings of openness. It helps in either mental, this development, mental well-being. At the same time, it leads to this creative or development of creative faculty inside the mind. So lots of ubiquitous things and exciting things in materials are happening in the future. This the major theory is these materials are becoming more and more AI-enabled or artificial intelligence-enabled material sensors combining with lots of IoTs, Internet of Things, gadgets, sensors, numbers of sensors, different types of sensors. I am breathing, and when I'm exhaling, then whatever from my body, what is coming out, my body odor and all these things, that can be captured at the wall, and immediately the wall panel will analyze all these things and can sense these my health parameters everywhere. So these are even when someone is entering to your home, surveillance, then facial recognition, how these persons look like, whether sentimental analysis, whether the person has good intention or some bad intention for entering to your room. So these all are happening, and what are the things behind it? One is materials, another thing is information technology of the future. These two are giving a formidable, unique combination for transforming the entire things, for transforming our entire lifestyles, our way of living, our way of communications, everything of even our garments, our textiles, our shoes, our frames. This Google Glass, all of you have heard probably Google Glass. This specs that will be a computer. That already in 2013 Google launched the project, though it was not successful. But 2018, another young chap from Arizona named Avinash, he designed it. with some, this Arduino, the chips and all these things. That is now reality. So many things, in future, we are going to enter in an era where all this smart material will interact with us. Now people have started experimenting or putting some inserts inside, augmenting our brain capacity by putting chips inside the brain. There are many devices which are already being placed inside our body, inside our, these arteries, inside our eyes, inside our, this replacing our bones and all these things. So materials are getting inserted in our body. So far, these materials are not that smart, but in near future, smart materials are coming, which will augment our capacity further, our physical capacity further. Maybe certain part of our hands that may be replaced by smart steel and all these things to make my hand more strong, effective, and these are called era of cyborgs. Within 2030 and 35, we may not be there, but all the participants who are here, they will be having a wonderful experience on this world so long you will be living. And I believe that this is going to happen. Lots of changes are there. Of course, it depends on whether the earth will be living with us or not, because of these global changes, climatic changes, and all these devastating things which can happen in near future. This virus, the mutated virus in more deadlier forms, all these things can happen. But let us be optimistic. Let us remain with the hope that we will overcome all these present problems and difficulties and problems in the future as well. But the point is that phenomenal technological advancement has happened in the last few years, and which will be which will be accelerating further and taking us to a new era, a new dimension. People will, if human being may reach to Mars for setting up colony, or to moons, there will be hyperloop concept. Cars will be coming without any driver, drone taxi. So, the list is innumerable. Innumerable lists are there. So with this, this future is very, very exciting. Only thing, you acquire right set of knowledge, skill, and ability to take up the challenge of this new future. This is my advice to all the young participants and students who are present over here.
Thank you, sir. Thank you for your very courageous speech to us. I think all the participants, young participants, will be motivated from your words. So now moving towards the end of the program. So now I am requesting Professor Ananta Kumar Das, Professor of Department of Environment Science, Makaut, to deliver the vote of thanks. Sir, over to you.
Thank you. Our Honorable Vice Chancellor, Professor Dr. Soikat Moitra, the most eminent speakers or panelists of the day, Dr. Anup Kumar Chattopadhyay, Dr. Polash Kumar Haldar, Dr. Soubhik De, Professor B.B. Poira, Professor T.K. Paria, Kunal Chaudhary, and other faculty members, students, and other participants from the other institutes and universities. On behalf of the organizing committee, I express my sincere thanks to our Honorable Vice Chancellor for a wonderful, motivational inaugural and keynote speech, and later on the beautiful concluding speech. He always motivated us with his continuous and enormous encouragement, support, and mentorship in organizing the webinar, and also for the total development of our esteemed university. It is my great pleasure and privilege to propose vote of thanks on this occasion. First of all, I convey my heartfelt thanks to Dr. Anup Kumar Chattopadhyay for his wonderful and absorbing speech on smart ceramic material. He has nicely elaborated the very first development and advancement in ceramic material and their applications in different devices. I convey my thanks to Dr. Polash Kumar Haldar for his doctoral research speech, sharing his work on generation of transition metals in doped zinc aluminate advanced ceramics. I also convey my sincere thanks to Dr. Soubhik De for his good presentation on his research topic for awarding PhD on generation of novel muellite and its composites based on bauxites and fly ash. I also extend my thanks to the webinar committee of the university, administration, and all officials of our university who took responsibility for communications, invitations, technical support in organizing this program, and also for the constant cooperation. I convey my heartfelt thanks to systems, especially to Prem Kumar, for his perfect digital support and guidance, staying behind the screen throughout the program to make it successful. I heartily congratulations to all the participants for their active participation in the events and patient sharing throughout the session and participating in discussions and question session. I extend my regards and thanks to Professor B.B. Poera, advisor of the university, for beautiful valedictory speech, and Professor Dr. T.K. Paria, director of the School of Energy and Environmental Science, for introductory speech and arranging this webinar platform with such a pool of experts. This webinar could not be accomplished successfully without their support and cooperation. Last but not the least, I must thank Mr. Kunal Chaudhary, is the faculty of this department, who all the times stay with us, given his beautiful starting of the program, and finally he has done his best for this department all the time. So I will call it a day of adorned with knowledges. Thank you very much to all. Thank you.
Good night.
Sir. Thank
Good
you.
night. Good night.
Thank you, sir. So, dear participants, we have actually shared the feedback and certificate link in the chat box. You can see that and fill it for getting the certificates. So, and this is the, as our Honorable Vice Chancellor has said, this is the beginning. So, we'll do series of programs on this particular topic in near future. So, so be connected with us and join the future programs. So, with the permission of the Honorable Vice Chancellor.
So there are certain questions I can see. Say, have you replied it? What is the current future of refractory industry? One fellow Sagar De, he posted this question twice.
Okay.
The future of refractory
Yes.
industry is always bright. We need lots of steel for these constructional purposes, for urbanizations, for rapid growth of infrastructure, and all these things. And more we consume the steel, more refractory requirement will be there. Maybe in different formats. Maybe refractories of the future will be more, sustainable. Less consumption of refractory will happen per ton of steel production. But refractory of different, these compositions, mostly high-performing materials, combining value-added materials with the precision manufacture systems, with the applications of all these modern technologies and tools in the refractory industries will happen in near future. So refractory industry is linked with steel industry. So if the steel industry grows, steel industry's growth is very high, refractory industry of course will flourish, because these are related industries.
Together with ceramics and all.
Ceramic has certain other markets, but refractory particularly, most of the market is associated with steel production. Steel, of course, there are other metals also, aluminum and other metals. For this metallurgical process, for metal, particularly steel, aluminum, and all these metallurgical processes, so long the market is good, the refractory market is good. And so long the construction process will go on, from the urbanization, infrastructure development will happen, refractory market will always be there. So future of refractory is good, but the refractory which were there at earliest days, maybe 10, 20 years before, may not be there in near future. We have to look forward new generation refractory comprising of high-tech materials, synthetic materials, these unshaped, tailor-made refractories. So lots of, this innovation will happen in the field of refractory.
There is another question, that is, what researches are going on regarding the recycling of ceramics from the green environment point of view?
Recycling of ceramic is there, particularly for refractories and potteries. Certain parts of pottery items, they are being used in tiles and sanitary wares. And refractory market is also there. Refractory market, these worn out refractories, all these things, these are process taken for making it as a raw materials further in making further refractories. So this reprocessing is there. You may call, but 100% recycling is not happening, but that people are working on that to make it 100% by making, this, because after the processing, after an operation part is over, when the material is put in production, it gets contaminated with many, these impurities, because out of these are, this outcome or offshoots of these production systems. So as a result of which, yes, many of the parts cannot be used, but people are working to differentiate the level of utilization of these, these waste materials. Lots of researches are happening. Lots of organizations are coming out for utilizing these waste materials, because these are becoming industries which you call B2B, one from one business to another business. These are becoming raw materials for other industries. Sometimes for the same industries it is being used, for sometimes it is going to other industries, because there are people are working to develop different ranges of products for these products for consumption by people of different levels. Sometimes rural, for consumption at rural beds, sometimes consumption for low valued item. So for different applications, people are trying to use all these materials. Till now, this is not 100%, but of course, this level of reutilization is increasing day by day. This is the biggest part. Even glass industries also, broken glass pieces are used as raw materials in glass making glasses. For tiles making, it is called tiles and sanitary ware, so pitcher. They are using it. In refractory also, they call it grog. So but you see the technical terms has come for utilization of all these waste materials. Level is increasing day by day. On an average, you can tell that around 40 to 50% are being utilized. 50% people are working to make it 100%. Maybe the days are not far away.
Thank you, sir. Thank you for your answer. So I think, sir, there is no extra other questions remaining in the Q&A.
So good night.
Sir, with the permission of the Honorable Vice Chancellor, sir, shall we end the program?